Thank you. I am Connor Cox. I work for United Conveyor. We are a material handling company, and that includes many of the ash conveying systems that Brandon mentioned, as well as dry sorbent injection and activated carbon injection systems. So I'll be presenting today on a few different DSI options for high levels of SO2 removal. And if Brandon was the presentation just before the graveyard shift, I guess that means that we have now begun. So we'll see if I can keep you awake. So the three case studies I want to talk through are highlighted here, and for each one, I'll talk through a unit and a DSI system description, the SO2 reduction performance for each, balance of plant effects, and lessons learned. The first will be on a 600 megawatt unit using Trona for their sorbent. The second will be on a 400 megawatt unit using sodium bicarbonate, SBC. And the third will be on a 350 megawatt unit using hydrated lime for SO2 removal. Well, there we go. So, case study one, using Trona for SO2. Once again, 600 megawatt unit. This unit burns PRB coal. It does include an SCR and a cold side ESP. They have an HCI system for their mercury removal, and the ash is landfilled on site. The DSI system consists of inline milled Trona injection at the air heater inlet. They have 4 silos, each over 120 feet tall. A common stair tower serves all 4. The silos are filled using a railcar unloading system, and they're unloaded using a screw feeder rotary airlock design. The conveying air from the rail unloading, for the rail unloading system, as well as to convey to the duct, is all conditioned with dehumidification and heat exchangers to reduce the temperature. And those are all to help optimize the sorbent usage in the duct. The milling is done using UCC's Viper mills. This system includes 2. There's a blower building, electrical building, and mill building. All were constructed on site for this system. So the silos being 120 feet tall required a 2-piece design that was welded on site. They have bin activators underneath, and all of the equipment inside the silo was installed on site. Today, that's atypical. Usually we have that equipment installed when the silo arrives on site, but when we installed this equipment, we provided that separately. So underneath the silo, just very simple feed equipment, a screw feeder to meter the sorbent into the conveying line, and a rotary airlock underneath to serve as an airlock between the positive pressure conveying line and the ambient pressure feed system. I'll get into this a little bit more in the upcoming slides. The Viper mills here have operated for just about 3 years with no significant issues due to wear or downtime. So a very successful operation of the mills. The reason for using mills with Trona is highlighted here. The reaction between SO2 and these sodium sorbents occurs on the surface of the particles. By reducing the particle size, you're going to drastically improve the performance and the usage of your sorbent. So what you see here is that an unmilled, and this is typical for Trona, an unmilled Trona sample typically is between 30 and 50 microns on a D50 basis. Coming out of the Viper mill, we see between 9 and 15 microns. So that will increase the usage of that sorbent by approximately 50%. The conveying and unloading systems here all, as I said, use conditioned air. So what you see here is in the top left, those are blower packages. We have bottom right is showing a dehumidifier skid with a cooling coil. So air passes through the coil, takes out the easy moisture, drops the temperature, and then goes into a desiccant wheel, as shown on the top right, where the moisture is further reduced to the proper conveying properties. From there, it goes through the blower, which increases pressure and temperature. We want to bring that temperature down so it does not affect our Trona. So we use air-to-air heat exchangers, as shown in the bottom left. This is just showing the injection location, and actually the two sets of lances you see here are activated carbon and Trona, so they're very close together, and I'll touch on that a little more in the upcoming slides as well. This system was controlled via the plant DCS. We can also supply these using PLCs. And this slide is simply to highlight the ability to remove SO2 with Trona. The site I've shown here is included in this data, but what you see is Trona can remove upwards of 90+% of the SO2. Now those are increasing injection rates along the way, obviously, but it is capable. For this particular unit, what you see here, and there's two curves, and one of them may be a little tough to see, but the dark blue data points and trend line are the data that we generated on site with our demonstration equipment prior to designing permanent systems. Before that demonstration, we did CFD modeling to confirm the lance placement, make sure our distribution was optimal. And what this shows is with a temporary system, a temporary setup, we were able to get virtually the exact same curve that we got with the permanent system. So that's exactly what we want to do with our demonstrations. That's the goal, the purpose of the entire thing is to generate the data we can use for a permanent installation. So for this case study, the balance of plant effects, air heater, since we were injecting prior to the air heater, that was one concern of the customer. We did not see any effects, which is typical for SO2 DSI systems. ESP, they initially found that ash was building up in some of the hoppers and assumed it was due to the DSI system. And it was possibly made worse by the sodium injection and the higher sodium content, but they found that water was leaking in every time it rained, and so it was building up with or without the sodium. The sodium just helped highlight the problem. Otherwise, there was no increase in particulate or opacity, and once again, that's typical for sodium injection with ESPs. The ash handling, the system obviously has to be able to move extra product. For Trona, your solid loading increases approximately 75% of your injection rate. So this system was able to handle that. And there were no landfill issues reported. Mercury removal, as has been shown in other slides already, it was affected when we began injection of Trona. And initially they required up to 3 times more activated carbon to reach the same mercury limit. They were able to nearly eliminate this effect by separating the Trona and the activated carbon. So the inside and outside of the duct is how they ended up doing it. Both are injected prior to the air heater, so by having activated carbon towards the center, Trona towards the outside, you increase that residence time where they can kind of work on their own before the air heater mixes everything together. HCl was also seen as a co-benefit. You see the dark blue line here is the HCl removal versus the red trend line being SO2. HCl you see doesn't change much because that's nearly 100% removal. So there's nowhere really to go at that point, at these high injection rates. Lessons learned here were a few. First, we did have uncontrolled Trona feed into the system, and that was mostly when we would fill the way hopper. The product would just flow straight through the screw feeder, so we had to tighten down those clearances, and that helped solve that problem. We were also overpressurizing the outlet of those screw feeders, so by improving venting, you allow the screws to feed properly as well. The control system, loss and weight system had to be tuned, logic tweaked, relatively easy changes there. And because this system was designed for future regulations and higher injection rates than they currently run, the silos actually store the product for a long period of time. And they found that with the breathing that the silo gets as it heats and cools throughout periods of days and months, moisture would begin to build up in the silo, and so then plugging occurs in the silo splitters lances. So by keeping a small amount of compressed air flowing into the silo when you're not unloading to it, you keep it from breathing by keeping it always just a little bit positive. And that's helped that issue drastically. This is just highlighting the uncontrolled feed. You see that at the top there is right after you fill a hopper, it flows right through the screw and it slowly comes down to the desired injection rate. So by actually retrofitting these inserts shown on the bottom right into the screw feeder, we were able to tighten down that clearance and eliminate that problem. And I mentioned the Trona activated carbon interference, but there's also some wear on the hoses between the splitters and the lances. We're providing new wear-resistant hose to improve the wear life there, and also working on routing the hose to reduce the bends, eliminate those wear points. For case study 2, it's a similar large DSI system using SBC this time for SO2 removal. This unit is a 400 megawatt unit. They burn PRB coal. They actually have a hot side ESP and then a fabric filter. Fabric filter was installed when they were under the assumption that they would need a dry scrubber, and I'll come back to that here in a little bit. They have an ACI system that is injected prior to the air heater. The ash is actually landfilled after mixing with the product from the fabric filter, as well as the byproduct from another unit's FGD. The DSI system here, once again, consists of a Viper milled product, this one using sodium bicarbonate at the air heater outlet. This has 4 silos, 100 feet tall each, common stair tower. This is using truck unloading versus a rail car unloading. Rotary airlocks are providing both the airlock and the variable speed feeder. There is a blower and electrical building that was fabricated on site, as well as a mill building. The truck unload and conveying air here are conditioned similar to the first case study with dehumidifiers and heat exchangers. Because these silos were 100 feet tall, the max is about 105 feet, we were able to construct these in one piece, delivered to site. They do include a chisel bottom, which is our standard for DSI and ACI silos. And all equipment in these silos was once again installed on site. This unit employs 3 Viper mills due to the once again, future regulations that the system was designed to. They actually only need to operate one at a time, but in the future there is a potential that they will need more than one. We've had approximately 2 years of runtime with only minor issues, and I'll once again talk about that in the lessons learned section. For sodium bicarbonate, the reason for milling is even more evident, as shown here. Really, the particles for SBC, especially when considering the price of the product, really just are not effective on their own at removing any appreciable amount of SO2 unless you mill them. The unmilled product as delivered here is about 180 to 250 microns D50. Out of the mill, we're between 12 and 15. So that drastically improves your performance, increases your surface area. This is just a photo inside the blower building. You see blowers in their enclosures. Whoa. Jumped ahead on me. All right. So the data shown here is actually generated once again during a demonstration prior to the installation of the full-scale equipment. And what you see here is very high removals, above 90%, and actually UCC guaranteed greater than 90% removal for our guarantees for the system. The demonstration was done because the plant wanted to compare to the economics for a dry scrubber. And on a 20-year life cycle, they determined that dry sorbent injection was the way to go for them. And that's using inline milled sodium bicarbonate as described here. An NSR of 1, what that's showing here is an NSR of 1 was getting us greater than 85% removal, which is very good usage of the sorbent. So balance of plant effects. The fabric filter, we saw no increase in particulate emissions or opacity, so that was good. Ash handling, once again, sodium bicarbonate, you actually add about 70% in solids, and it was able to handle it. It was a polishing bag house, so the majority of the product in that hopper is the sodium bicarbonate, so they learned not to let it build up for too long, and as long as they keep it moving, it didn't cause problems. No landfill issues were reported. Like I said, they blend this with a number of other sources. They did see an NO2 plume, which is relatively typical for sodium bicarbonate in a bag house. And you're just because you're oxidizing NO, creating a little NO2, and it's a red-brown plume that's apparent. And the way the plant is handling that at this point is by injecting a little more activated carbon, because the activated carbon actually absorbs NO2 similar to how it absorbs SO3. So the activated carbon actually takes care of it. For mercury removal, as I said, they inject a little more carbon, but still greater than 95% mercury removal was achieved. The lessons learned here included a tweak to the filter and oil cooling design for the mills in the lubrication system. What we found was during the polar vortex, when it was very cold, there were some issues with the temperature of the oil getting to the mill. So that was tweaked to alleviate that problem. And that was the only problem that's really been reported at this site. So third, another large DSI system using hydrated lime for SO2 removal. This unit is a 350 megawatt unit burning PRB coal. They have a fabric filter, an HCI system, and the ash is landfilled. This DSI system includes hydrated lime injection at the air heater inlet. There are 2 silos with a common stair tower. They use trucks to deliver, so it's a truck unload system. They have a screw feeder rotary airlock design where the screw feeder provides the variable speed to adjust the feed rate. Both the truck unload and conveying air are conditioned. There is space that was designed into this system for future Viper mills should the plant ever decide to switch to a sodium sorbent for higher SO2 removals. But currently they do not employ Viper mills and they're using hydrated lime. There is a blower building and electrical building that were actually prefabricated. The system's designed for a high reactivity hydrated lime, not a specific manufacturer at this point, but the upgraded product. And they use UCC's COBRA Lances, which I'll get into a little more as well. The splitters used here, similar to the other units, include an auto purge system. So the splitter itself has a static mixer and a proprietary insert to help get accurate splitting and eliminate areas where buildup can occur. Typically, when plugs happen in DSI systems, they are in the small feed lines. The smallest lines that you get are downstream of the splitter because you're trying to split to a number of locations to get better dispersion. So our auto purge system, it senses those plugs as they occur, purges them as needed. They can also purge daily as these do for just a maintenance item. And it just clears those soft plugs, makes sure they don't build up and get hard and harder to remove. The COBRA Lances, shown here on a skid, and I've got more slides here on these, are to improve the distribution immediately at the injection location. This is important for short ducts, for hard ducts where you have a turn immediately, you need to get dispersion to allow the product to interact with the pollutant that it's targeting. This one you could find on YouTube if you look up United Conveyor COBRA Lance. It simply shows how they're installed, how they operate, how they're expected to operate. This video is actually this one is one that a customer supplied where they, while it's operating, showed what a standard lance looks like as hydrated lime is fed into the duct. And then this one shows similar operation with the COBRA Lance. You can see even in these slides the distribution that you get immediately after the injection location. And that just highlights how effective those lances really are. For this customer, changing from a standard lance to a COBRA Lance was approximately 23% improvement in sorbent usage. So they used 23% less sorbent for the same emissions level. So very significant. And this was just data that we generated in the demonstration at the unit for case study 3. This was actually a standard hydrate product. They wanted the system designed for a standard hydrate, not necessarily a top-of-the-line hydrated lime. So what you see here is we were achieving greater than 50% removal with a standard product. And with those injection rates, you see just how low HCl goes. As you increase, the removal increases as you would expect. Balance of plant effects the fabric filter. There was no increase in particulate emissions or opacity. Mercury removal, saw that you may need slightly more activated carbon due to some interference there, but they're still evaluating the full-scale system operation data. The systems are just being commissioned and getting operating at this point. So that's all I have for today. If you have any questions, I don't know how we are on time. Yeah.
I was just wondering, when you're feeding the compressed air to prevent the breathing in the silo, is that up somewhere or in the silo or down around the pant leg?
So we have fluidizing that we run occasionally through the product. It's down, it's actually in the bottom of the chisel. But for the solution here, we were actually feeding it in, you tap it into the roof of the silo. Because really all we care about is that the air is moving out of the bin vent and not coming
in. In your milling, because I've done some testing years ago, and I always wondered about milling, but do you get the product that does it plate out on the milling elements at all, that you have to go periodically and clean it off or scrape it off? Or
Yeah, so UCC actually has a patented cleaning system that's automatic. It uses water to clean the mill. Typically, we recommend once a day, just as far as maintenance goes. We've operated for up to 9 days without cleaning. And it's approximately a 45-minute cycle between stopping feed, running through the cleaning cycle, drying it out, and then back to operation.
And finally, one more. On the COBRA Lances, do you get a lot of erosion from the flue gas? Is that?
So far, we haven't seen that. And we use materials that, and we've used a number of different materials at this point, depending on the flue gas constituents, fly ash, so on. But we haven't seen a lot of erosion at this point.
On the unit that you had that you injected the Trona before the air heater, did that have an SCR on it with ammonia injection?
John? Yeah, no, there was not an SCR.
Stop. Have you guys done any studies like, my plant, we have the SCR, but we have a lot of slip, and we get a lot of ABS into our air heaters.
Mm-hmm.
What's the effect? Would that Trona increase, decrease that effect versus hydrated lime? Because when we get to that fact, we actually go above some ports in our air heater and dump hydrated lime into it to try to clean it out.
Yeah, I think, John, correct me if I speak out of line here, but I think you would see a similar effect with Trona. I think the thought process is your ABS is forming when you get ammonia reacting with SO3, and so by removing that SO3 with Trona or hydrated lime, both would be effective. You would not see the ABS formation. All right, thank you.